So good morning, everyone. Welcome back to Math 115. So I thought we'd start off special Tuesday Thanksgiving session by looking at some of your amazing drawings. Um, so I found that many of you, well, okay, there were maybe about half of the class who attempted to draw a shark butt, and they fell into, I think, four camps. The first camp was the anatomical camp, anatomically correct camp, who drew something like this. But then there was various other approaches in terms of if there was a butt, was it on top, like with the dorsal fin, or would it be down, kind of hanging beneath like an udder? So I'll show you what I mean. Oh yes, and then there was the camp that thought maybe it would just have a butt instead of a tail, which was also great. Let's see. This one I didn't know what to make of. I think this might be a rear view. From the back? Okay, nice. Yeah, that one was good too. This one I thought was just a great drawing. And they said no butt, just shark. Was that you? That was really funny. Yeah, here's the shark butt on top. Okay, I think this one is more savory than the shark butt on bottom. This one just this one just felt kind of wrong. Let's see. Oh yes, I liked this one. This is another in favor of the butt on top. More butt on top. Oh yes, there was. This one was pretty good. I thought this was just kind of some kind of shark man. Okay, more in the anatomical camp. Oh yeah, this one was interesting. This was kind of like a rear view of a bottom camp.
He's called tailbone for a reason.
Yeah, this one. Come on, just no. All right, and that was it. So I hope you all enjoyed looking at those as much as I did. It was like every time I would grade an exam, I would be looking forward to getting to the end of the exam so I could see what was on the final page. That's what I love about grading exams.
Process for the shark butt question, though.
For the shark butt question?
Yeah.
I actually Googled that. I have a bunch of questions that I like to ask on exam bonuses. I almost always do the what was something that you thought you knew but it turned out you were wrong or something like that. I almost always do that one because that one's fun. That one gets a lot of really interesting responses. Okay, so let's start for today. So today I'm going to talk about section 5.4, actually, 5.4. You have a couple of homework assignments which are due on Tuesday after the break. And you're going to have a quiz on that same Tuesday. It'll be a group quiz. You can work with a couple other people on that quiz if you want. If you need to communicate with me vis-a-vis office hours this week, I need you to send me an email so that we can set up an appointment for a remote meeting. Other than that, there's the tutoring center. And yeah, that's all I have to say. Are there any administrative questions before we start in on content for today? Okay, if not, then we can start in on today's class. So let me remind you what we talked about last time. What we talked about last time was we finished up the sum and difference formulas, which basically tell us how to, another way in which we can kind of break things up. It allows us to do cosine and sine of some sort of less friendly angles, right? Less friendly angles. As long as you can write those less friendly angles as a sum or difference of friendly angles. Okay, by friendly here I mean they make a 45, 45, 90 or a 30, 60, 90 when we inscribe them inside the unit circle. Those are the friendly ones, which I can find out the side lengths of that triangle and thus the values of each trigonometric function. So we have these sum and difference formulas, which are useful now and again. Yeah, but not nearly as useful as what we learned next. Oh, never mind. I forgot about the cofunction identities, which again, I feel like we already knew this, which is to say that, look, you can do a transformation of sine and get cosine, because just visually looking at the graphs, they look at like exactly the same thing except kind of moved over, right? So you might imagine that there exists a transformation. The special transformation pi over 2 minus x is the transformation such that if you use it for either one of them, then you get the other function, which is kind of interesting, I think. It's saying more than just you can transform one into the other and the other into the one. It's saying you not only can you do that, you can do it using the exact same transformation for each of the functions. That's kind of interesting. It just tells you how closely related these functions are. Okay, so then we learned the most important formulas that you will learn if you're going to go and take a calculus course. Well, at least if you're going to go and take a Calculus 2 course. Probably. And definitely if you go beyond that. So what are they? There's double and half angle formulas. So they tell you basically how to do kind of this power reduction. Okay, so typically the way we want to use these in calculus is in this direction as a power reduction. Okay, and that's useful because later on you're going to want to do integrals like this. Okay. And these two integrals will be the same because the integrands will be the same. Except the integral on the left is intractable, okay? It's not really something you can do. The integral on the right, however, is very easy. Very, very easy to do. So this is the utility of these for calculus. But we're not going to talk about integration. We're just going to talk about how we can use it, which is, again, kind of the same flavor of thing as can be done with these sum and difference formulas, which is to say that, look, we can sort of expand the class of angles which we can do. Not only can we do things like pi over 6, pi over 4, pi over 3, pi over 2, we can also do things like sums of those angles. Or we can do things like half of those angles, okay? Half of those angles we could do. Okay, so say you wanted to know not even what is sine squared of pi over 12. You could do what is sine of pi over 12. Let's do that really quickly. How would I do sine of pi over 12? Well, I could rewrite sine of pi over 12 as the square root of sine squared of pi over 12. And I could rewrite sine squared of pi over 12 as 1 minus cosine of, I multiply pi over 12, the angle here, oops, forgot 1, pi over 12 by 2, because that's what's inside cosine here. So it should be twice the angle on the left-hand side, which was pi over 12, so twice that is pi over 6 over 2, and then we draw a unit circle. Pi over 6 looks like 30 degrees, which is more to the right than it is up, which means we're like square root 3 over 2, 1/2, okay? So cosine is going to be the x-coordinate, which is square root 3 over 2, so we get the square root of 1 minus the square root 3 over 2 over 2. Or if you want, you can simplify that a little bit to like 1/2 minus the square root of 3 over 4. Okay? So that's the utility of the double and half angle formulas for us in the pre-calculus course. But I want you to have seen them if you go to a calculus course because they are amazingly useful when it comes to doing integration using trigonometric functions. Okay, are there any questions on what we talked about last time? Yeah.
Can you explain why you how you know how to square that?
Sorry?
Can you explain how you know you're supposed to take the square root of?
You mean how do I know to do this?
Yeah, like how do you know that you're supposed to? Yeah.
Okay, so here's my thought. when I see this, I think to myself, I'm screwed. I can't do pi over 12. I can then go one of two routes. I can say, well, I know that if I were to apply this identity, the angle would be twice what it is right now, which would be pi over 6, which would be an angle which I know how to do. Does that make sense? That's one methodology. Another methodology would be to say, look, you could do it this way, or you could say, look, this is the same as sine of pi over 4 minus pi over 6. And then you could use the difference formula for sine. That would be another way, because pi over 4 minus pi over 6, what would that be? That'd be 3 pi over 12 minus 2 pi over 12, right? That would get us pi over 12. So you can rewrite the angle, right? Because you know that pi over 12 is the difference of pi over 4 and pi over 6, which are friendly angles. Or you can say, look, this is sine of pi over 12 is, if I multiplied this with itself, then that would give me sine squared of pi over 12, which would be equal to whatever this is. So if I take the square root on both sides, then one of these powers goes away, and I'm left with just sine of pi over 12. Does that answer your question? Am I going like really into too much length there?
Yeah.
Still a little confused?
I'm just confused about like why you take. How do you know you take the square root?
Because the square root and the power will cancel out.
Exactly. So, okay, so I could say the following. Like, if I know x squared is equal to 5, right? Then I could say I know that x would be equal to the square root of 5, right? But I can also go in the other direction, right? Or in this. Okay, I understand what you're saying. It's sort of abstract reasoning. But my goal is to apply this identity, which says that sine squared is equal to this jazz. What I have is not sine squared. So what I say is, look, sine squared okay, let me give myself more room to work here, because this is a good question. It really takes some foresight to be able to see why we should do this. My thought is the following. My goal is to figure out what is the number y. Agreed? This implies the following. Do you agree with me? I can square both sides, because these two numbers are the same. You square them, again, you get the same number on both sides. Yes? So my goal is, look, what I want to do is solve this equation. But I can instead solve this equation and then take whatever y squared is. That would give me what y squared is. And then I could figure out what y is by just taking the square root of whatever that is. Does that make sense? So so this one, I don't really have an identity I can apply unless I use a sum or difference identity. But this one, I can say, aha, well, this is just 1 minus cosine of pi over 6 over 2. If I look at this thing here is equal to this thing here by the identity, yes? So therefore, this is equal to y squared. So if I want to know what y is, I'm just going to take the square root on both sides of this equation.
Why is it cosine of pi over 6?
Why is it cosine?
Like a pi over 6.
Because the pi over 12 gets multiplied by 2. 2 times pi over 12 would be pi over 6? Good question. Yeah, that's sort of the whole point of the double angle formulas is you double the angle, right? The angle was pi over 12. We double it. That makes it pi over 6. Is this more clear now that I write it like this? Okay. Any other questions on this example here? Okay. What I promise is on the exam, okay, if I ask you to use identities to solve a trigonometric equation or something like that, I will not tell you specifically, like you must use the double angle identity or you must use a sum or difference identity. I will say use whichever identity you want. Fair? Okay. But some of them will probably be far easier to do using one identity as opposed to another. Usually that's true. Any other questions on sum and difference identities or double angle identities before we move on to the new section? All right, then we're going to skip a section. We're skipping 5.4. I forgot to mention that at the start of class. And we're going to go to 5.5. Because 5.4 is like more identities, which are honestly I've never used in my life, so I'm not going to make you learn them. What I have done many times is solve trig equations. So I will skip that and move forward in order to try to give you the best and most well-rounded pre-calculus education I can, so you're as prepared as possible when it comes time to do actual calculus. So, what are trig equations? Well, we've already learned about identities, trig identities. And the difference between an identity and an equation is identities are always true for all x. Equations, on the other hand, are sometimes true, depending on the input x. So usually, with equations, the big question is, which ones make it work? Okay, so let me show you an identity, and then I will show you an equation. Here's an identity. Okay, here's an example of an identity. Why is it an identity? No matter what I plug in for x, this is always going to be true. If you take that number, add 2 to it, and then square it, it's going to be the same as squaring it and then adding 4 times itself and then adding 4. You can see why this identity is true because FOIL, right? Basically FOIL. X squared plus 2ab or sorry, a squared plus 2ab plus b squared is what I meant to say. Okay, so this is an identity. It's true for every x value. Here's one that's not true for every x value. This is an equation. Specifically, it's a quadratic equation. What do we like to do when we have something like this? We want to find what x values can I plug in that will make this to be true. So what we do is we would say this implies that x is equal to -2, makes the equation true. Right? So that we've already been doing this for quite some time, finding the x values such that if I plug them in, the statement is true. Okay, we've been doing it all the way since probably the first day of class. So that's the difference between an identity and an equation. So far for trig, we've been learning a ton of identities, things like sine squared, of x plus cosine squared of x is equal to 1. These are always true, right? Always, always true, no matter what x value you put in. But there are such things as trigonometric equations, which will not always be true, but they will sometimes be true. We've already seen them here and there. So let's take a look at one of them really quickly as an example. So here's a trigonometric equation. It says sine of x is equal to cosine of x. This is not a statement of fact. It is an equation, and you can find the circumstances under which it will be true. Okay? It will be true some of the time. And the question we want to answer is, when will it be true? By which I mean, for what x values can I plug in such that the value of sine and cosine will be the same? So I can view this in many different ways. Here's one way. You can view this as, well, look, the x values are all lined up here on the x-axis, right? I know that the value of sine x and cosine x will be the same when the graphs have the same x value and the same y value. In other words, where does the graph of sine intersect the graph of cosine, right? These are the points where these two graphs cross one another. That's one way of thinking about this. And I could describe all of the x values for which this is true. Okay, I could describe all of the x values for which that is true. Another way to think about it would be to look at the unit circle. What do we want? We want a point on the unit circle whose x value is the same as its y value, right? That's what we want, which happens in two places. It can't happen here because here the x value will be negative, but the y value will be positive, so they can't be the same. Here, again, same reason, but reversed. But down here, you could have something like negative x, right? And if these were the points, then you could do the following. You could say, look, these are points on the unit circle. X squared plus x squared equals 1, 2x squared equals 1, x squared equals 1/2, x equals square root 2 over 2. So this is the point square root 2 over 2, comma square root 2 over 2. And of course, plus or minus, right? And then this is the point negative square root 2 over 2, negative square root 2 over 2. So what do I want to do? I'm supposed to describe, oh, and I have made a big no-no here. Let me change this to t. Okay? What I mean when I say I've made a big no-no is I use the letter x when x was already reserved as the input. Okay, I'm changing the input now. The input should be t. So I want to find the input t such that the output of sine is the same as cosine. I know that that happens for points which are the point square root 2 over 2, square root 2 over 2, or negative square root 2 over 2, negative square root 2 over 2. My job is to describe the angles which point at those points. So there's this angle, and there's also this angle. So those 2 points would be t equals to pi over 4 and t equals to 5 pi over 4. Yes? Okay, but here's the thing. There are even more angles which will cause the equation to be true. Can someone give me one more angle which is going to cause sine of t to be equal to cosine of t? That's not pi over 4 and not 5 pi over 4? Are there any others? Let's go back and take a look at the graph. What have we said? We said at pi over 4 it's going to happen, and at 5 pi over 4. Let's go look at the graph. We're looking for the points where they intersect. Here's pi over 4. Here's 5 pi over 4. Are there any other intersections? Yeah, later on, right? Here and here. And guess what? The graph is going to keep going, right? And they're going to intersect again. How many intersections do you think we're going to have over the course of the entire real line? Probably unlimited, right? Infinity. So what are the other angles? It's not just pi over 4 and 5 pi over 4. What would the next one be? Close. 8 pi over 4 would be 2 pi, which would point straight to the right.
9 pi.
Yeah, you want 9 pi over 4. And then 13 pi over 4. And so on and so forth, right? So we've also got 9 pi over 4, 13 pi over 4, dot, 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 right? Dot, dot, dot. Okay, so what we want to do is describe the set of all t values for which the equation is true. And we do that using set builder notation. So let me just first quickly describe set builder notation. So this is notation. If I say something like this, okay, this is the set of all numbers x such that x is bigger than 2. Okay? That would be one way to do this set. Okay? So the anatomy of this notation is to say, look, first you put the variable of what this thing is, and then you're going to say one of these colons. That means such that. Okay? Or sometimes people will do a little line like this. That's fine too. And then this means the rule, which your number must abide by. Okay, so this is a rule in which the number has to be bigger than 2. But I could do one for this, which would say the following. T is a number such that t is equal to pi over 4 plus 2 pi n, or t is equal to 5 pi over 4 plus 2 pi n, where n is an integer. So I do one of these little z's. I could do something like this. This would be a set builder notation where I say, look, I want my number t to satisfy the following. It needs to be equal to pi over 4 plus some multiple of 2 pi. What does that give us? That gives us all of the angles whose terminal point is this point up here, right? So here's pi over 4. There's also 9 pi over 4. There's also 17 pi over 4. Yeah, and so on and so forth, right? So that incorporates all of those angles. And then this one says, look, you take also the angles 5 pi over 4 plus any multiple of 2 pi. That gives us all of the angles which point down here. Okay, so not just 5 pi over 4, but also negative 3 pi over 4. Also negative 11 pi over 4. And so on and so forth. All of the angles. Okay, so what we want to do is, this is kind of like when we did inequalities, right? We had to give our answer in terms of interval notation. Because what are we trying to do? We're trying to describe an infinite set of numbers. We can't just write them all down, right? We can't just write all the numbers down. We have to say all of the numbers will look like this, where n is like some integer, like 1, 2, 3, 4, 5, 6, or negative 1, 2, 3, 4, 5, 6, or 0, right? You could actually you could make this even simpler by doing the following. You could rewrite this set in the following way. You could say actually just t is equal to, oops, not equal, t such that t equals pi over 4 plus n times pi. That would be another way to say it. It's a much cleaner way of writing it that I just realized. Oh, such that t is equal to that, comma, n is an integer. So what does this one say? You say, look, t has to be pi over 4 plus some multiple of pi. If you add 1 pi, you get to here. If you add 2 pi, you get to here. If you add 3 pi, you get to here. If you subtract pi, you again are down here. If you subtract 2 pi, you're over here. If you subtract 3 pi, again, you're back here. Is that clear? So that's a cleaner way of writing it, probably, that I just didn't notice the first time I saw this. So many different ways to write the same set, okay? Any questions on this so far? So basically, the answer to the question, when is sine t equal to cosine t, is, look, it'll be true as long as the angle points at one of these 2 points. There are infinitely many angles which point at each of these 2 points. So we have to come up with a way of describing what are those angles looking like. Well, they look like pi over 4 plus a multiple of pi. Okay? Any questions on that before we move on? Okay, I'm going to do one more example and then we'll do partner practice. Okay, so let's do another one. Oh yeah, so let's describe what is the basic plan of attack for a problem like this. Okay, is look, you're going to find all the solutions which are between 0 and 2 pi. Okay, namely what we did for this one, we found pi over 4 and 5 pi over 4. And then of course, we know that there are many other angles which also point at those same points. So by periodicity, we can add 2 pi to any of the solutions, and we're going to get another solution. So we just take basically all of the solutions which are between 0 and 2 pi, and then we say, look, plus 2 pi n for each of them. Plus 2 pi n. You can add multiple of 2 pi, I'm going to get the same angle. Okay, it's going to be coterminal. Is the strategy kind of clear? How do we feel about this strategy? Thumbs up if we're like, I'm ready to try it. Thumbs down if less than happy. Ian? Are you good? Okay. All right, let's do I'll do one more example for you, and then we'll work on a partner practice, okay? Find all x values such that if I plug it into the sine function, I get 1/2. Now this is a bit of a different question. This is a very different question than this question. This question is asking you for one specific number. It's the number such that sine of x is equal to 1/2 and x is between pi over 2 and negative pi over 2, right? That's the inverse question, which we said we had to add this special restriction to the inverse problem in order for it to be solved uniquely. But now we're not trying to solve this uniquely. We're trying to find a way to describe all of the possible x values which make this true. Okay, so let's try. Here's what I'm going to do. I'm going to draw a unit circle. And what does sine of an angle give me? If I take an angle and I plug it into the sine function, what will it give me? Well, I would put the angle in the unit circle, right? And then what's sine going to give me back? The y value of the point on the unit circle. So what do I know? I know that x is an angle in here. And it points at a point on the unit circle whose y value is 1/2. Okay? Whose y value is 1/2. If the y value is 1/2, I can figure out the x value easily. Using this. So x squared is equal to 3/4. Therefore, x is equal to plus or minus the square root of 3/2. So there's 2 points on the unit circle such that the height is 1/2. The first one is square root 3/2, and the second one is negative square root 3/2, and the height, of course, for both of these points would be 1/2. Okay? So 2 points on the unit circle whose height is 1/2. Now, my goal is to describe the angles which give us these 2 points. The first angle is pi/6. Okay, that's this angle. What about this angle here? What's this angle? The pink angle, which gives us again angle, yeah? Yeah, this one's 5 pi/6. Okay, you can tell because this height here is 1/2, which means this height has to be across from a 30-degree angle, which means that, okay, you know that this whole thing is pi, and you know that this part here is pi/6. So you take away pi/6 from pi, you get 5 pi/6. Okay, so that's how we get that angle. So these are the 2 angles which are between 0 and 2 pi, which cause this to be true. So what is my solution set going to be? My solution set is going to be x such that x is equal to 5 pi, sorry, not 5 pi. Why don't we do pi/6 first? X is equal to pi/6. That's the one which is between 0 and 2 pi. And how do I get all of the other coterminal angles which will point at this point but go around the circle like however many times? I need to add something. I need to add 2 pi. That would get me the one which goes around once. How about the one which goes around twice? I'd have to add 4 pi. Or if I went around 3 times, I'd add 6 pi. So what I really want to add here is not just 2 pi, but 2 pi times n, where n is any integer. Okay? Or, so I'm going to write or, x is equal to 5 pi/6 plus 2 pi n, where n is an integer. Is it more clear after the second example?
Are you allowed to use words in a test, like or and where?
Yeah, sure. If you're using set builder notation, you can basically do whatever you want. I mean, technically you could also just use a comma here. Or if you really wanted to, you could say, if you wanted to be super good about your notation, probably here's what I would do. I would say x equals pi/6 plus 2 pi n, comma, n is in z, and then I would close that and I'd do a union, and then I'd do x such that x equals 5 pi/6 plus 2 pi n, comma, n is in z. If you wanted to use like very precise mathematical language, that would maybe be a better way of writing it. But it's fine. What we want to do is just describe, look, I have a bucket here. The bucket is denoted by these squiggles, right? And I need to tell you what I'm putting inside the bucket. As long as it's clear to me what's inside the bucket and what's not, I'll be happy. Something like this is clear, right? It's all the numbers x equals pi/6 plus 2 pi times any integer. all the numbers x equals 5 pi over 6 plus 2 pi times any integer. Okay? Any other questions? All right, then let's do a partner practice. So go ahead and group up with somebody. We're going to work on 2 different problems here. The first one's not bad, but the second one is hard. Okay? But I think you can do it. Okay? I think you can do it using the hints. So let's take the rest of the class, okay? We're going to work on these together, and I'm going to float around and try to give you help as needed, all right? Lane, can you work with Maya, please?
Yeah.
Thank you. And then Andrew and Griffin. Yeah. Caroline, Connor. All right.
Did you give out the test?
I did, yeah. Do you want yours?
No.
I'd appreciate it. If you did not give me a test.
Did you not get yours? Oh. Here's yours. Here's yours. Mm-hmm. I'll be back in a sec, y'all.
We can move right now. We can move on.
Okay, how's it going in the front? Okay, well, one thing I do want to say is we can't actually bring that in, right? Here's why. This is a function, right? So we're multiplying 2 times a function, which actually means we're going to change like the function height, right? If you bring it inside, it's actually going to change this vertical transformation into like a horizontal line, right? Okay, so we want to keep the 2 on the outside. But what do we want to do? Let's take a look at this one. This one was easier, right? Just one trig function, sine x equals a half. We can actually take something like this and make it look a little bit more like that by just get rid of the 2. The 2's annoying, right? Move over to the other side. Then what would we have? Well, it's being multiplied here, so you have to undo multiplication with division, right? So we could get cosine, and then we still have x minus pi over 2 equals 1/2. So, whatever we put inside here, okay, should be an angle which gives us an output of 1/2 for cosine, okay? So whatever this number is, needs to be an angle which gives us 1/2 for cosine, okay? So let's figure out what angles would give us 1/2 for cosine, okay? 1/2 would be the x coordinate of the point. What would the y coordinate be? √3/2. You know what angle that is?
That's like 30, 60, 90.
Yep, and specifically, if 1/2 is the x coordinate, we're gonna be having a 60-degree angle, okay? So that's one situation in which the angle inside would give us 1/2 as an output of the cosine, is if this angle, whatever x minus pi over 2 is, gave us pi over 3, okay? What's the other angle that would give us an x, or, okay, what's the other point on the unit circle whose x value is 1/2? That would be the height, yes, the height would be negative square root 3/2. So this would have the same x value, 1/2, but the y value would be negative square root 3/2, right? So what do I want? I want the angle, okay, I want this angle to be either this angle or, as you say, this angle, right? But we can easily express those angles. So let's start with writing an equation, x minus pi over 2. We want this to be equal to whatever this angle is, this angle here. That gives us a point here with x value 1/2. Does that make sense? So what's 60 degrees in terms of radian? Wait, so we want the input to be pi over 3. Does that make sense? Okay, so let's put pi over 3 there. So ultimately, we want to say what x should be, right? We know that x minus pi over 2 should be pi over 3. How should I figure out what x is going to be then? Yeah, just add pi over 2 to both sides, right?
Yeah.
Okay, so let's do that. Add pi over 2 over this side. We can cancel it out here. Common denominator, right? This one becomes 2 pi over 6, and this one's 3 pi over 6, so together they make 5 pi over 6, right? Okay, so good. We figured out the input, x here, such that if I plug it in here, this would become pi over 3, and therefore cosine of pi over 3 would be 1/2. That gives us the angle corresponding, the angle input corresponding to this point here. But there's one other point in there. How would I solve this second equation? So maybe a good first step would be figuring out what is this angle which goes down and points right here. Pi over 6 would be in the fourth quadrant, or third quadrant. 11 pi over 6 would be right here.
This one's even worse.
Okay. Where would 9 pi over 6 be? That's right. Is that 9? No. Let's do 9 pi over 6. Tell me what that would simplify to. 9 pi over 6. If you simplify this, what would you get? Where's 3 pi over 2? Straight down. So I need to go a little bit more than that sometimes. How much more than that? What is this angle? You know that this triangle here has a 60 here, 30 here. What's this angle then? 30 as well. So what's 30 in terms of radians? Pi over 6. So we need to go pi over 6 more than this. There you go. Now you got it. Is that clear? What I was just going through with them is, look, to go to here, that's 3 pi over 2, which could be rewritten as 9 pi over 6. We need to go an additional pi over 6. So what we want is for the input here to be 10 pi over 6. So we're going to make an equation like this one that goes x minus pi over 2 is equal to 10 pi over 6. Actually, now we're going to get another answer, right? After that, it's just some set builder notations, okay? Okay, that's true, yeah. You can always just get some info by over Google, right? Okay, well, this is a great first step, right? The first step, because like, now it's like, before, right? The 2 just kind of throws us off. I'll do that too. Now we got cosine of x minus pi over 2 is equal to 1/2. I'm trying to find the x values of cause this to be true. This would be a whole lot simpler if this said like cosine of x equals 1/2, right? Then I know what x values cause the width of my point to be 1/2, right? What I need is a point whose x value is 1/2, which means that the y value has to be square root of 3 over 2, which is bigger than that, right? Which means that this angle is gonna be what? 60, right? Or pi over 3. So what I want is for the input to be pi over 3. The input is x minus pi over 2, right? I want that to be equal to pi over 3. Does that make sense? Right. I'm just not good at writing upside down. Okay, so if x was a number such that if I subtract pi over 2 from it, I get pi over 3, then when I plug that number into cosine, I would definitely get 1/2. Does that make sense? So what x value is going to cause x minus pi over 2 to be pi over 3? Yeah, how do we need to solve this equation? Just add pi over 2 to both sides, right? And then how do I add pi over 2 with pi over 3? Common denominator, right? Pi over 2 would become 3 pi over 6. Pi over 3 would become 2 pi over 6. Added together, what do I get? 3 pi over 6 plus 2 pi over 6 is 5 pi over 6. Okay, so that's the angle, such that if you put it in here, the input would become pi over 3, and that would cause this equation to be true. Are there any other points on the unit circle whose x value is 1/2? It'd be down there, right? So if I was gonna draw this, now I need to figure out, well, what would be the angle which goes to there? That one's pi over 3, right? So you need to take pi over 3 away from 2 pi. That's okay, it's kind of confusing. see what input x would cause x minus pi over 2 to be that input. Because that input, if we plugged it into the cosine function, would give us a half. Okay. So we're going to do another equation kind of like this, right? Where we're going to do x minus pi over 2 is equal to what? 5 pi over 3. Okay, so then we get x is equal to, let's see, we're gonna get something out of this. Okay, so the first one we can solve in the following way. I want cosine of x minus pi over 2 to be equal to 1 half. Okay, I divide both sides by 2. And then what do I want? I basically want whatever this input is, call it t. Okay, I want that input t to be an angle which gives me an x value of 1 half. So I'm looking for the intersections of the unit circle with the vertical line x equals 1 half. There are two intersections. The first intersection is for the angle pi over 6. So what do I want? I want t, whatever the input is, to be pi over 6. Not pi over 6. What the hell am I talking about? Sorry. Pi over 3. Which means I want x minus pi over 2 to be pi over 3, which means I want x, if I add pi over 2 to both sides, to be, I think it's 5 pi over 6. Is that right? Yes. Okay, so that's one option. The other option is the angle here, which is the angle 5 pi over 3, right? 5 pi over 3. So we want t is equal to 5 pi over 3, which that is x minus pi over 2. Add pi over 2 to both sides. We get x should be 13 pi over 6. Okay? So these are the two angles which are between, actually they're not between 0 and 2 pi, but these are two angles which uniquely define a point on the unit circle, and we get both of the points whose x value is 1 half. To get all of the other angles, here's what I'm going to do. I'm going to say x such that x is equal to 5 pi over 6 plus 2 pi n, or 13 pi over 6 plus 2 pi n, where n is an integer. Okay? So this gives us the collection of all the possible points. What I want to talk more about is the second one, because the second one is pretty damn hard. I'll use a whole page for this one. So this one we can rewrite. Okay, the hint said to rewrite sine squared theta as 1 minus cosine squared theta. If we do that, okay, then we can distribute that 2 and collect like terms to achieve the following. So, all I did here was distribute the 2 onto the 1, put it together with this number, okay? And then I distributed the 2 onto the negative cosine squared to get negative 2 cosine squared. I left the middle term completely alone. Now, the trick here is to recognize that this equation is quadratic in form. Namely, if x equals cosine of theta, you can rewrite this equation as negative 2x squared plus the square root of 3 times x plus 3 is equal to 0. This equation can be solved using the quadratic formula to get, what would it be? Negative b plus or minus the square root of b squared would be 3 minus 4 times 3 times negative 2. That's plus 24, right? Did I do that? 4 times a times c. 4 times 3 is 12 times negative 2 is negative 24. I thought this would work out a little bit better than this. Over 4, right? Over negative 4. So I'm going to just make that a plus. Okay, so now what do we do? This is going to become x equals the square root of 3 plus or minus 3 times the square root of 3. Here we go. All over 4, which means that x is equal to either 4 square root of 3 over 4, which would be just square root of 3, or x is equal to negative 2 square root of 3 over 4, which is equal to negative root 3 over 2. And you immediately throw this one out, because remember, x is equal to cosine of theta. Okay? X is equal to cosine of theta. Cosine can never be square root of 3. It's too big. So you get rid of that one, and now we are left with the following equation. We want to find theta such that cosine of theta is negative square root 3 over 2. That one, I believe you can do it. Okay, I believe in you for that one. So, very tricky problem. Quadratic in form is back with a vengeance. It takes quite a bit of mathematical reasoning to do this one, so I think I'm over time, so I'll stop there. All right, have a good break.